Hello, now we will start the third part of this first module. We have seen the law that the equation that we will make use in order to calculate the physical and the chemical exergy of the stream of mass of the system that we are analyzing. So now we can apply this equation to the real case. So we will start with the first stream, which is easy to calculate in terms of, we will see now, the physical and the chemical content of exergy. So the first stream in this plant is the stream of air, so the stream number 0, 2, and 3. The physical, the calculation of the physical exergy is quite easy. You remember it is the gradient of enthalpy between the thermodynamic point of your stream and the restricted state minus T0 by the gradient of entropy. So, because we can consider it as an ideal gas, this can be transformed, the gradient of enthalpy and the gradient of entropy, in this very famous equation for the gas stream, ideal gas stream. So the specific heat by the gradient of temperature, which is the quantity related to the enthalpy gradient, minus T0 by a first element, which is the normal logarithm of the temperature of the stream divided T0, the temperature of the restricted state, plus the gas constant of the gas by T0 by the logarithm of the ratio, in this case of pressure, between the pressure of the gas and the pressure of the restricted state, P0. So you see the calculation is definitely very easy. In terms of chemical exergy, air is definitely the stream which is which represent most of the biosphere. So we can say the air is by definition already in chemical equilibrium with the biosphere. So a stream of air is already chemically in equilibrium with the biosphere. If you have a stream of air, for example, the molar flow, the molar fraction of oxygen is exactly the same molar fraction of oxygen that you have in the biosphere. So you have no gradient at all. So the chemical exergy of the air is 0 because it is in equilibrium with the biosphere. If we move to the exhaust gases, the situation becomes a little more tricky because so we are talking of the streams number 4, 5, 6, and 7, which have all the same chemical composition, remember. So in terms of exergy, physical exergy is quite easy because both, again, this stream can be considered as a stream of ideal gas, so you can make use again of the equation that we have used for the air. So the gradient of enthalpy, which is related to the specific heat by the gradient of temperature, and the gradient T0 minus T0 by the gradient of entropy, which can be expressed as a ratio of temperature and a ratio of pressure. So we know this type of equation. But the chemical exergy is a little more tricky. Why this? Because if you have a stream of mass, to calculate its chemical exergy, remember that you have to take the stream of mass that is in a whatever thermodynamic condition you want, you have. So let's say the stream of mass is at 1000 degrees and 10 bars. This stream of mass has to be taken and put in equilibrium with the dead state. So put it in the condition said as restricted dead state. This equilibrium is only a physical equilibrium. Still, to calculate the chemical exergy, you have to calculate the remaining disequilibrium. You have to consider the remaining residual disequilibrium in between your stream of mass and the biosphere. But remember, the stream of mass has been put in physical equilibrium with the biosphere, so in T0 and P0. When you take a stream of mass and you put it in equilibrium with the biosphere at a usually lower temperature, which is T0, and a lower pressure, which is P0, something can happen, modifying the physical state of some of the chemical species that you have in your mixture. For example, if you have components, chemical species that can condense when they are cooled down, you have to take into account that part of your chemical species will be found when you put it in equilibrium with the biosphere, in a different state of aggregation. So can be partially, to be concrete, to be clear, can be partially condensated. The classical chemical species that usually in the usual stream that we use in the most in thermodynamic system, the classical chemical species that can condensate when cooled down is water. So we have to consider that this phenomena will occur. This stream of mass in condition 4, 5, 6, and 7, when put in condition T0, will be partially modified, not chemically, but physically. Part of the water will condensate. So what we have to do is to consider the molar fraction of the molecule that for sure will not condense, so which are gas in the biosphere condition. In this mixture, the molecule that will not condense for sure are oxygen, CO2, and nitrogen, not condense when put in equilibrium with the biosphere, I mean. So you have to consider the molar fraction of these three components and to sum up to the stable gas total molar fraction, which is around 92%. After, move to consider what happens to the water. So the water will, when the stream will be put in equilibrium with the biosphere, partially will condense. So we have to calculate how much of the water will remain in equilibrium with the gas in form of steam in the restricted state, and how much of the water will condense in form of liquid. So to do this, we have to calculate, to first consider the saturation temperature, the saturation pressure of water at the temperature of the dead state. If I consider the temperature of the dead state 298.15 Kelvin, I know that the partial pressure of saturation of the pressure of saturation of water is equal to 0.0317 bar. So now, if I consider 1 kilomole of mixture in the only gas phase, so considering the water which has remained in mixture in form of gas with the other stable gas, oxygen, CO2, and nitrogen, we can calculate the partial pressure of this mass of water still in form of gas with this simple ratio of molar moles multiplied by P0, which is the pressure in the state that we are evaluating. The number of mole of gas has been already evaluated because it is this one. Given a kilomole of gas, you will have 0.9248 kilomoles of stable gas, which is this amount, not condensing gases. So at the end we will have that the number of mole of water that are still contained in form of gas, I can say, or form of steam, in equilibrium with the not condensed gases, can be considered calculating the saturation pressure of this, the water at this temperature by the number of mole of not condensed gas divided the pressure in the dead state minus the saturation pressure of the water at the temperature of the dead state. And you will obtain 0.0299 kilomole of water that will remain in form of gas. So, with a sum up of this, at the end, when you take this stream and you put in equilibrium with the dead state, you will have oxygen will remain with its molar fraction 0.14. CO2 will remain with its molar fraction of around 2%. Nitrogen will remain of its molar fraction of around 79%. No, 75, it is not there, sorry. And water that will have a molar fraction of 0.0299, that it was the one calculated now as the molar fraction of water remaining not condensed. So the total of the gas, summing up oxygen, CO2, nitrogen, and water not condensed, now is equal to this value of 0.954%. All the remaining part of the water has been condensed in liquid form that has now this molar fraction. Okay, so consider now the not condensed gas. Now, this, in order to calculate the molar fraction of this stream of not condensed gas, you have to normalize the molar fraction of all the 4 components towards the value of the not condensed gas. So if you normalize this 0.14 towards the value of the total not condensed gas, you will obtain that the molar fraction of oxygen will move from 0.14 to around 0.15. The same will occur for the other chemical species, CO2, nitrogen, and steam. Now this is the composition of the stream which has remained in form of gas. And over this composition you can apply the equation that we have described before. So the chemical exergy of a stream of gas can be calculated as the sum over the molar fraction of the chemical exergy of every single chemical species by the universal gas constant, by the temperature of the dead state, by the sum over the molar fraction of the logarithm of the molar fraction of the chemical species into the stream that you are considering. These molar fractions are the one listed in this table, you see. 0.15 for the oxygen and so on. These are the values that you have to input here. The value of the chemical exergy of the chemical species can be found from a tabulated value. So for this you can find your reference in terms of literature. In this case I have considered to use the tabulated values that are contained in the book of Bejan, and especially the model 2 of the table contained in the book of Bejan. So I have selected a given value in terms of joule per mole of the chemical exergy, specific chemical exergy of the oxygen, of the CO2, of the nitrogen, and of the steam in form of water in form of vapor. By substituting all these values, I obtain at the end the chemical exergy of this stream of mass equal to 358 joule every mole. Of course, we are not concluded because remember, we have still to consider the last part of this stream, which is the water in liquid form. So the water in liquid form has its value of chemical exergy. Again, I use the same value, I said the same reference, which is the table of Bejan in the model using the model 2. And I obtain a value which is 900, I take from this table a value which is 900 joule per mole. So I have all the data. The stream of gas in condition 4, 5, 6, 7, when I want to calculate its chemical exergy, is composed of 2 contributions. The contribution of the gas phase, 358 joule per mole. The contribution of the liquid phase of water, 900 joule per mole. I have to sum the 2 contributions, of course, weighting across the molar fraction of the gas phase and of the liquid phase. Remember, the molar fraction are this one. This is the molar fraction of the gas phase, this is the molar fraction of the liquid water. So, going back, this is the calculation, 0.95 by the chemical exergy of the gas phase, 0.04 by the chemical exergy of the liquid phase. It gives a result of 383 joule every mole. Finally, I can obtain it in the mass basis. I have only to divide the chemical exergy in form of moles, so joule per mole, by the molar mass of this stream of exhaust gases. And dividing this, I obtain the value of 13.52 kilojoule per kilogram. So this is the final result of this long calculation. I can say it is most difficult to calculate the chemical exergy of this stream of gases. At the end, we have only to calculate the exergy of the stream of the water, condition 8 and condition 9. The physical exergy of the stream of water can be obtained through its definition, so gradient of enthalpy between its thermodynamic condition and the thermodynamic condition of the dead state, minus T0 by the gradient of entropy. So remember, this is water, we cannot use the equation that we have used for the ideal gas. Chemical exergy, a stream of water whichever is your state, can be steam, but when it is put in equilibrium with the restricted state, this stream of pure water will completely condense. So the chemical exergy of a stream of water in which whatever is its thermodynamic condition, its chemical exergy is the chemical exergy of the water in liquid form, because in the restricted state the water will completely condense. So it is the value that we have already considered of 900 joule per mole. At the end, so the very end is the calculation of the chemical exergy of the stream of fuel, so the stream number 1. You know, the stream of CH4 is in disequilibrium with the biosphere, both chemically, especially I can say chemically, but also physically, because remember this stream is available at a pressure of 12 bar, which is in disequilibrium physically compared to the biosphere of 1 bar. So first you calculate its physical content of exergy through the usual calculation. Second, you calculate the chemical content of its exergy. This will be definitely the highest value of its contribution to its exergy, because it is really chemically in disequilibrium. And this can be calculated as the relationship that we have already analyzed. Gradient minus gradient of the Gibbs free energy of the reaction. So the Gibbs free energy of CH4 plus the Gibbs free energy of oxygen minus the Gibbs free energy of CO2 minus the Gibbs free energy of the water, which are the product of the reaction. The reactant, CH4 and oxygen, minus the product of the oxidation reaction, which are CO2 and water. Of course, all the molar Gibbs free energy are multiplied by the stoichiometric coefficient of the reaction. So 2 for oxygen and 2 for water. Plus the chemical exergy of the product of the reaction, which is CO2 and water, you see, multiplied by the the stoichiometric coefficient in the reaction, minus the chemical exergy of the reactant of the reaction except the fuel itself, so except CH4. So minus 2 times the chemical exergy of the oxygen. So at the end you obtain a value which is around 824-720 joule every mole. So you see, very high value. If you want to pass to the mass quantity, you have to divide by the molar mass of the molecule of CH4, which is 16 gram per mole, and you will obtain at the end the value of 51,406 kilojoule over kilogram, which is, as you see, a quantity which is definitely very close to the value of lower heating value of the molecule of CH4. So this is why they say that considering a fuel like CH4, the calculation of its chemical exergy content at the end give you a result which is very close to the lower heating value of this molecule. So in most of the case you can make, especially in big type of large analysis, very complex, you can make an approximation to approximate the value of the chemical exergy of the fuel to its value of lower heating value of the molecule. So this is a thing that can be accepted in long calculation. But anyway, you see, this is the rigorous way to calculate the chemical content of exergy of a molecule in complete chemical disequilibrium with the environment, like a molecule of fuel. So this is the end of the third part of this module 1. Now we will move to the module 2, in which we will make analysis of the result of the analysis of the gas turbine CHP configuration case study.